Hello, and welcome to our next set of stats notes. We're on section 4.2. We're going to deal with some specific rules for dealing with certain situations when you're finding probabilities, specifically the addition and multiplication rules. Each of these has its own uses, certain times when they come up and when we use them. So we'll deal with both and talk about why we use them. So for started off, we'll look at the addition rule. So the addition rule is used anytime we want to find the probability of one or another, or it could be both. So you're looking for two different options. It could be option A or option B. Either one will make you happy. This is like when you're playing cards and you want all the same suit, or you want, another card that's going to be like a 10 that's going to complete your set, your run. So maybe the 10 of hearts will be, it's good because it's both part of your run, but it's also a heart, and you're looking for hearts. Or any other heart would help you get your hearts, or any other 10 will help you get your run. So you might be happy with a 10 or a heart, whichever one. If you're playing, a game like that, if you're playing blackjack, you might be happy with the jack or an ace, because either one's a good starting card, and you're on the right track for getting 21. If you play blackjack. But just an option, an idea where two different options, both are good, and you're happy with both of them. And you're looking for the probability of finding either one happening. So this is probably of one or another. The big word here is or. So what we do is to find this probability. The probability of that happening is the sum of the probabilities of the events. So the different events. Find the probabilities of each one separately, and then subtract the probability of both happening at the same time. So this is the way we write the rule. The rule is if you want to find the probability of A or B, so we're looking for either one, A or B would both be good. Find the probability of A, find the probability of B, add those together. Now, when you do that, stuff that's part of both sets, something that's in both sets got counted twice, so we always subtract the probability of something being in both sets. What's the overlap? So that's the idea. So when we're doing this, find the probability of both parts and subtract. And this is for OR probabilities. Again, we subtract the probability of both happening because we really counted that twice. We counted it for both sets because anything that's in both sets, both A and B, well, we counted for A, we counted for B. We ended up counting it twice, so we subtract that overlap. So let's look at a couple examples. I think once you see some examples, it'll make a lot more sense. So first off, let's find the probability of rolling two dice, and they could either be both odds or they could be both evens. So we'd be happy either way. If they're both odds or they're both evens, either way we're getting something that's going to help us win or whatever. So we're happy either way. So the big thing here is that word or, so that either one's good. So to find the probability of both odds or both evens, those are the two events I'm looking for. Either the event they're both odds or the event they're both evens. Again, what I do is I find the probability of each one separately. So I'm going to find the probability of both evens first. Then I'm going to find the probability of being both odds. What are the chances I get both odds? Second. And then I'll take those and add them together, and I'll subtract any overlap, something that's both. So first up, I look at for both evens. Well, what are both evens? That'd be things like 2-2, 2-4, 2-6, 4-2, 4-4, 4-6, 6-2, 6-4, 6-6. Those would all be options that are both evens, right? There's actually ends up being 9 of them, so there's 9 options that are both evens. Notice that there are 6 by 6. When you roll two dice, there are 36 total number of options. So there's 36 options, so 9 out of 36 is my probability. Remember, probability is always number of good results. Well, there's 9 that are both evens out of the total number of possibilities, and there's 36 total possibilities. The second part, to find my both odds, I'm going to look at things that are, both evens, things that are both even. So I'm going to look at, I did that backwards. I wrote them down backwards over here. Wow, I swapped things up. I don't know why I swapped them up here, but I did. Yeah, I swapped them down here. So we'll do this in odds. Sorry, both odds. So I'm looking for both odds now. I'm looking for 1-1, 1-3, 1-5, 3-1, 3-3, and 3-5, 5-1, 5-3, and 5-5. So this is both odds. And it ends up being 9 of those as well. That's being the same. There's 9 things that are both odds out of the 36 possible events. 9 things and both odds. Now, I always subtract overlap, but in this case, you'll notice that there is no overlap. So when I go to subtract to find out what's the probability of being both even and both odd, and find out there's nothing that fits that set. You know, if you're both odd, like 1, 1, you can't be even. If you're both even, 2, 2, you can't be odd. So this is nothing. There's nothing out of the 36 that work. So in this case, we actually don't have anything to subtract because there is nothing that is both even and both odd. You know, there's things that are both even, there's things that are both odds. There's nothing that are in both of those. So when I subtract, there's really nothing to subtract. So I really only have to worry about the adding part for this problem. So I do 936 plus 936, I get 9 plus 9 is 18. Remember when you add fractions, you only add the top, so the bottom just stays 36. And then that simplifies. You can simplify that 1836 to divide top by bottom by 18. You get 1 and 2, I believe, if I'm thinking about this right. Yeah, because 1/2. Yep. So 1/2 is our answer of your probability. Or you could do 50%, 0.5. That's the idea. So when you find a probability of or, this or that, you find the probability of each one separately, and then add those together. If there's any overlap, if there's anything that's in both sets, then you subtract. So let's try one that actually has some overlap, so you can see that as well. Let's try probability has overlap. So this probability this time we're going to find things that sum up to 4 or things that are a pair. So I'm looking for things that add up to 4 and things that are a pair. I'm going to do those. So I'm looking for probability, finding sum of 4 or a pair. And again, to find the probability, when we have or, we find each one separately. So first I'm going to find the probability of things that sum to 4. So I'm going to look for things that add up to 4. Well, things that add up to 4 are things like 2 and 2, 3 and 1, 1 and 3. I've got, what is it? I've got 2, 2, 1, 3, 4 and 0, but we can't do 0. So I think that's it. There's only those 3 options that are both, or that are things that add up to 4. So things that sum up to 4, there's only 3 options out of all those 36 options. Only 3 of them add up to 4. Then I do the next part. So now I'm looking for things that are a pair. So I'm going to find the probability of things that being a pair. So where 2 numbers have to match. That's going to be things like the 2, 2, those match. 1, 1, 3, 3, 4, 4, 5, 5, 6, 6. Those things all are pairs. So that ends up being 6 of those, right? 1 for each number, 1 through 6. So there's 6 that are pairs out of the 36. But I do notice that, when I was doing these two, I ended up doing that pair of 2 2s twice, right? Because they add up to 4, but they're also a pair. So this time I have some overlap to subtract. I'm going to subtract the stuff that is both. So sum of 4 and a pair. What is both? What is the sum of 4 and a pair? Well, there's only one thing, right? The 2 2s is the only one that is both sum to 4, because it's in that group, and a pair, which is in that group. So there's only one out of the 36 that's in both. So we're going to subtract that one, we're going to add these ones, and that will give us our answer. So that's the idea. When you're doing this or probability, you have more than one option that works. You find the probability of each option, add that together, but subtract anything that was counted twice. Because the pair of 2s got counted for both of these sets, so we don't want to really count that twice, because it doesn't count twice. You can't get 2 2s, the pair of 2s 2 different ways. You just get a pair of 2s, that's it. So that's why we want to add these up and then take away that extra pair of 2s. So 3 plus 6 is 9, minus 1 gives me 8. So I get 8 over 36, because again, you don't add the bottoms, just keep them the same. This one simplifies, both of it before, you get 2 over 9. So I believe you get 2 ninths for this one. Because 8 and 36 both divided by 4, and you end up with 2 ninths. So that's the idea. We found the probability here, but find the probability of each part and adding them together and subtracting any overlap. Okay. Now there's a special case where we might deal with something called disjoint events. So disjoint events, we say events A and B are disjoint, or another word for this is mutually exclusive. It's just a fancier word for it. If they cannot occur at the same time. So another way of saying that there is no overlap nothing to subtract. So there's nothing to subtract because there's nothing that counts in both situations. So that's what we saw in the first part of the first page, right? We saw when we did both odds, both evens. These ones, both evens, both odds, that was disjoint because you couldn't be both evens and both odds. You had to be one or the other. There was no overlap, so we had nothing to subtract. If that happens, you don't need to subtract. That's what happens. If the sets are disjoint, it's not necessary to subtract because the probability of both is 0. So that's what we see. We see that not necessary to subtract is that is 0 because this probability is 0 if it's disjoint. So this is special for disjoint events. So when you're looking at these probabilities, these OR probabilities, it's always good to note, is it disjoint? Because if it's disjoint, then you don't even worry about the overlap when you find the probability. If it's not disjoint, if there actually is overlap, then you need to subtract. So the next problem, we want us to find out if they're mutually exclusive or disjoint first, and then find the probability. So in this example, I'm drawing cards from a deck of cards, standard deck of 52 cards, which is a queen, a jack, or a 4 of spades. So I'm looking for a queen, a jack, or a 4 of spades. It could be any one of those, and it would count. You'll notice this time I actually have 3 things, and that's okay. You could still do these OR probabilities with more than just 2. So this one I added up to 3. For each separate one, you'll just have another thing to add. So I'm going to find the probability of getting a queen, so I'll put Q for queen, a jack, or a 4 of spades. So 4 of spades, cover all 3. But first, before I do that, I just decide, is this going to be mutually exclusive? Is it going to be disjoint? Well, since queens are not jacks, and neither of those are 4s of spades because they're not 4s, then yes, this actually is mutually exclusive. This is disjoint, so yes, it's disjoint. So when I do this, I won't have to worry about overlap. I'm just going to find each one separately, add them all up, and now give me my probability. So find this. I'm going to find the probability of getting a queen. I'm going to find the probability of getting a jack. I find the probability of getting a 4 of spades. I'll find each one of those separately. I'll add it all up, and now give me my answer. So I just add, there's nothing to subtract. So since this is disjoint, we do not subtract. There's no need. As soon as you find out it's disjoint, you can say, oh yeah, there's nothing to be shared. Queens are not jacks, they're not 4s. There's nothing in common. I don't have to subtract. Queens, note there are 4 queens in the deck of cards. The diamonds, the hearts, the clubs, the spades. There's 4 different queens. There's 4 queens out of 52 cards. Same thing with jacks, right? There's 4 jacks, just like there's 4 queens. The 4 spades is one specific 4. There's only one 4 spades. There's only one of those out of the 52 cards. And again, because we're finding OR, we add. So I don't care if it's the queen, the jack, or the 4 spades. Any one of those cards is going to be good for my hand. So I'll take all 3. So we add them up. At the top, 4 plus 4 plus 1 is 9 out of 52. Don't believe that simplifies. Nothing goes into 9 and 52, so we would just leave it like that. I'm not sure, you can always check it with a calculator, throw it in there and see if it simplifies. But no, 9 over 52 should not. Let's try the next one. Here I want to roll an odd or a number larger than 3. So odd or larger than 3. So odd, that'd be like 1, 3, 5, because we're looking at a 6-sided die. I forgot to say that. 6-sided die, so it's only 1 through 6. So odd would be 1, 3, 5. Larger than 3, well, that's going to be numbers like 4, 5, and 6. And so we look at that and we say, oh wait, 5 gets counted both times. So this one is not disjoint because there is something that's in both sets. So as soon as you find out it's not disjoint, we do need to subtract. So we're going to find each one and then we're going to subtract. And this is a pretty simple example. So with small sets of numbers, you could probably do this without using the formula. You just count all the options that work. Notice that 1, 3, 4, 6, and then one of the 5s, and that would give you how many good options are. But for more complicated situations where there's lots of things that might work or might not work, it's good to know this basic principle. If you're doing OR probabilities, you can break stuff down to an OR probability, this set or that set. You can always find the probability of the problem. Find the probability of something like an odd or greater than 3, by finding each one separately. So by doing probability of an odd first, adding the probability of a greater than 3 second, and then subtracting the probability of being in both odd and greater than 3. And that's the way you can break this down. If you ever have something where you have an OR probability, no matter how hard it is to count the parts of each set, you can break it up into an addition problem and a subtraction problem. In this case, yeah, there's only 3 odds. 1, 3, 5, those are the 3 odds we have. There's only 3 numbers bigger than 3, right? 4, 5, and 6. So there's 3 bigger than 3. Oh, it's not a 6. I don't know why I put 5 there. Sorry about that. It should be a 6. 3 out of 6. I think I hit that 5 there. 3 out of 6, because there's 6 sides on a die. 6-sided die. And there's 3 bigger than 3 out of 6 sides. And in the last one, there was only 1 overlap, right? The only overlap was number 5, so there's 1 in the overlap out of the 6 options. So we add and we subtract and get our answer. So 3 plus 3 is 6. Last one gives me 5. And keep the 6 on the bottom, and so 5, 6 is the answer. And again, you could look at this, and without even using the formula, you could count there's 1, 2, 3, 4, 5 options. You just got to be careful not to count the 5 twice. And that's why we subtract here, because when we do it this way, we find each part separately. We did count the 5 both sets. So by taking it away once, took away the 5 that we counted both times, we're left with just the stuff we need. Not counting the 5 twice. So we don't want to count twice. Okay. Next part, complementary events. We mentioned complementary events last time, so this is going to be kind of a reminder of what we said last time. Remember that complementary events are when 2 sets are, opposite of each other. So stuff that's complement of A is the stuff that's not A. So if A is odd, then complement of A is going to be the evens. That's the stuff that's not the same, not the complement. Because by definition, A and A prime complement, these 2 sets are disjoint. By definition, they are disjoint. Then the probability of the 2 separate parts, when you add it together, is going to be the whole set, because it's all the options, and there's no need for subtraction, right? We don't have anything that's in both sets. So probability of A or A complement is going to be 1, the whole thing. And we kind of mentioned this before. We said last time that if you find the probability of something and find the probability of its complement, together those always give you 1, the whole thing. So I kind of previewed that. Now this is helpful though for sometimes when you want to find the probability of the thing and it's easier to find the complement, you can just find the probability of the complement and subtract it from 1, and that'll find the probability of that event. Or vice versa, if you want to find the probability of complement, find the probability of an event, subtract it from 1, and that'll give you your complement, the probability of complement. So that's how we use this. A lot of times we'll look for a situation where it might be easier to find the opposite and then find the answer. So find the probability of an event by finding the probability of its complement and subtracting from 1. So that's what we'll do down here. So this problem says, the probability of A winning, we'll say A is winning, is going to be 35%, right? So 35%. They want to know what's the probability you won't win. So what's P of A complement? Because opposite of winning is not winning. How do we find that? Well, we said we can find the probability of A complement by doing, A complement by doing 1 minus the probability of A. Since probability of A is the probability of winning, we subtract 35%. Now don't subtract 35, right? 1 minus 35 gives you a negative. We know probabilities can't be negative. Remember that when you're dealing with a percent and 1, you want to make sure you turn this back into a decimal. So it should be 1 minus 0.35. And so then, yeah, of course, that would give us 0.65 or 65%. That's the chance of not winning if the chance of winning is 35%. This is something to do with lotteries and raffles and stuff all the time, is people are really bad about, understanding how bad their chances are. So instead of telling you what the chances of losing are, they tell you the chances of winning. Because when I say, hey, you have a 35% chance you might win, that sounds pretty good. You go, hey, 35%, that's a lot better than like 5 or 10%, maybe I'll win. But when I tell you, oh, but you have a 65% chance that you're going to lose, then it sounds a lot worse, like, oh, more than half the time I'm going to lose. Like, no, I probably shouldn't play this because I'll probably just lose. But that's one of the tricks that, they do. If you ever look it up, you can look up the chances of winning the Powerball, the lottery, and all that kind of stuff. They never publish the chances of losing because they don't want you to think about that. They want you to think about the chances of winning because that makes it look so much better. Okay. Now we're going to do the other part. So we said the addition rule. Now we're going to do the multiplication rule. But before I can get too far into the multiplication rule, we have to talk about a specific kind of probability, which is called the conditional probability or the given probability. So to do the multiplication rule, first have to note that sometimes we find probabilities that look like this. We have probability of B and then this bar and A. This is called the probability of the event B will happen. So it's probably the probability of event B given event A has already occurred. So we're looking at the fact that, oh, something happened. Now what's the probability of the next thing happening after the first part happened? For example, you're drawing 2 cards from a standard deck and you're asked to find the probability of a king given a queen. What this means is you're finding the probability of getting a king after you drew a queen. So for example, drawing a king after you drew a queen, that's what this is, probability of a king given a queen. Well, that means I'm looking for a king, and since I drew a queen the first time, there's still 4 kings left in the deck, right? Because I didn't draw a queen out. If I was looking for a king after I drew a king the first time, then there'd be like less kings, but there's still 4 kings in this situation. So I'd say, okay, there's 4 kings, but because I already drew a card, I drew a queen out my first draw, there's not 52 cards left anymore. There's only 51. And so my chances are actually a little bit better because they drew a queen the first time. The queen's already out of the deck, so there's less cards in the deck. So 4 out of 51, that's a little bit better chances than 4 out of 52. So this is different versus, the probability of a king without the given queen. So if I'm just doing a king on the first draw, that would be 4 out of 52 because there'd be 52 cards to start with. So a given probability is kind of tweaked a little bit, just changed a little bit based on what happened in the previous draw. So they drew a queen the first time, so now when they go to draw the king, there's only 51 cards left. Versus, originally there was 52 cards. If you tried to draw the king in the first place without the queen being drawn, it would be a little bit harder because there was 52 cards to draw from. Okay, so we use this given rule to find the probability of doing both A and B. This is when I want both things to happen. Now, this is a little different than the OR probability. With the OR probability, we're drawing like one thing. We're doing one event, basically. We're doing one pull, roll, die, something like that, and saying we have multiple options that work. But when we do and a probability like this, when we're doing the multiplication rule, we're actually doing more than one thing. We're going to draw 2 cards, not just 1 card. We're going to roll the die twice, not just once. That's a bit different here. If I want to do A and B, I'm actually going to do both A and B, so doing 2 steps. I'm going to try and get A the first time, because otherwise that wouldn't work. I need to get A for this to be true, for this to work. But then the second time, since I already got A, I'm going to try for B, given that A has already happened. So here we're looking at finding the probability of the second part, B, given the first part has already happened. What usually happens is when you do the first part first part A, when you do first part A, it changes the probability typically for B. So that's where you have to be careful. So once event A has occurred, the probability of B has usually changed. So when we find the probability of B, we must account for that change. That's the big difference here. So let's look at a couple examples. So first off, I want to find the probability of drawing a queen and a jack. So I'm looking for both the probability of getting a queen and getting a jack. I want both. I want the queen and then I want the jack as well. I want both cards to come up. To do this, first I'm going to find the probability of the queen, because the first draw, I need to get that queen. If I don't get it, it didn't work anyway, so I'm looking for that queen. And I'll multiply that with the probability of the second time of getting the jack, because now I'm looking for the jack, but I have to say given the queen already came out. Notice that this doesn't say anything about putting cards back, so I'm drawing both cards and not putting anything back. So we're going to say this is without replacement. That's important because if I put the cards back, then probability wouldn't change because every time you draw, you'd be drawing from the whole deck. We'll say without replacement, that means that when we go to draw that jack, there's not as many cards left. There's not all the queens in there that there were to start with, who drew one out. So without replacement means it changes over time. Okay, so we draw the queen. Well, again, there's 4 queens out of the deck. We said that earlier today. There's 4 queens out of 52 cards. And then we say, okay, if I drew one of the queens out, how many jacks are left? Well, there's still 4 jacks. That didn't change at all, just like the kings up above. Because I'm drawing a queen the first time and looking for a jack the second time, nothing changed on the number of jacks because I got a queen the first time. But now there's only 51 cards left because we already took out one of the cards, right? We took out the queen to start with. So given the queen means now there's less cards to draw from. And that's what we'll multiply to get our answer. Now, something like this, you could just multiply it as is, but these are going to be kind of big numbers. So you could save yourself a little bit of multiplication if you simplify. Remember, you can always simplify before you multiply. So I can look at this 4 over 52 and realize that both of these will divide by 4. So this gives me 1. 52 divided by 4 gives me 13. And that's just going to be a little bit smaller to multiply. 4 over 51 sadly doesn't multiply, or does not cancel. So we would end up having to just multiply as is. So 1 times 4 is 4. And then what is 13? 13 times 51 would be 663. So that's the simplified version of this. You can't go any further because we already simplified it before we multiplied. So that'd be the simplified answer for that one already. So again, if you're doing and, want both the queen and a jack. I'm drawing 2 cards now, not just one, and saying, oh, it could be either or jack or queen. No, I'm saying I'm drawing 2 cards. And I want the first one to be a queen, and I want the second one to be a jack. And that's my chances. That exact thing happens. Let's try one more like this. Is a good idea. So what's the probability? I roll 2 dice, and I roll a 4, and then an odd. So now you notice I'm rolling, 2 dice. I'm rolling first die and then the second die, in order. I could do this by rolling the 1 die twice and get, do the same thing basically. But because now I'm doing 2 things, this is an and probability here. I'm doing 2 things. I want them both to come up. So I'm going to do probability of getting first a 4, and then second an odd. Okay, so I'm going to find the probability of getting a 4. I'm going to multiply that, find the probability of getting an odd, but I have to do that given I got a 4 in the first roll, right? Because we're doing probability of multiplication where I say given the first thing happened, then find the probability of the second. And what's my chance of getting 4? Well, if I'm going to say, we'll say 6-sided dice. I didn't say that, but I should have, because there's lots of dice, right? If you play, D&D or something like that, I know there's like 20-sided dice and all that kind of stuff. We'll say 6-sided dice unless they specify otherwise. So we'll say 6 sides. So on the 6-sided dice, there is only 1 4 out of the 6 sides. And then look at the odds and I say, okay, what are my chances of odds given a 4? Well, in this case, it actually doesn't matter, right? Because when you roll a die, you're not changing the next roll, right? The first roll of the die or the first die doesn't change the second roll of the die or the second die. So in this case, this given a 4, it really doesn't actually matter. I just have to figure out what the probability of an odd is. Because this is a case where the second thing is not affected by the first thing. And that can happen. Sometimes the second thing is not affected at all. So in this case, we'd say, okay, what's the probability of getting an odd? Well, an odd is going to be 3, because there's 1, 3, and 5, we talked about earlier. There's 3 sides out of the 6 sides on a die, and that's our second part. So again, we don't care about the 4. This doesn't really affect anything. It has no effect. Okay, we multiply when we're doing and. So we're doing and, we multiply. Here again, we could simplify, right? We can divide this by 3 and get 1, divide this by 3 and get 2. And that's simplified before we go. So 1 times 1 is 1, 6 times 2 is 12, and that gives us our answer. So 1/12 would be our chances. You'll notice with these probabilities, the chances are a lot lower. Here, 4 out of 663, that's really low chances. 1/12 is a lot lower than 1/6. It's harder to do 2 things than just 1. So trying to get both things to happen is usually more difficult. So when you're doing and probabilities, you should expect kind of small answers because you're trying to do more than one thing. So it makes it harder to make it work. Okay, last page, we'll do a couple more examples. Now I do want to talk about independence. So when you're doing things, when you're doing these different roles or drawing cards or stuff like that, you have certain situations where we say things are independent. We say event B, the second event, is independent from the first event, event A, if the probability of B given A is equal to the probability of B. And what that means is that doing event A does not change the chances of event B. So having given A does not change anything. You could just find probability of B. This is what we just saw with the dice example, right? The first roll of the dice did not affect the second roll. And so in that case, we would call those independent. So independent, you say it's independent, event B is independent of event A if probability of B given A is equal to probability of B. So event A does not affect the chances of event B. That's when we say they're independent. Things like dice rolls are always independent because the first die roll does not affect the second one. Coin flips, so if you took like a 2-sided coin and flip it, the first flip does not affect the second one. Decks of cards where you draw cards can be independent if you put the card back in between draws. So if I draw a card from a deck of 52 cards, look at it, and I put it back in, they shuffle and have me draw again, the second draw is not going to be affected by the first one because all the cards are back in the deck. So things like that where put the card back in, you replace it. Things like dice rolls and flipping coins, those are independent. We saw on the previous page when we pull a card out and we don't put it back, we keep it out, we say without replacement, that would be dependent because in that case, the first draw does affect the second draw. There's less cards in the deck, so it changes the chances. So let's look at this. So here we go, drawing a jack, a 4, and a jack, and we're going to say without replacement. And as soon as we see those words without replacement, we know we're not putting the card back. We know that this would be dependent. So dependent is just the opposite of independent. So dependent, the chances change. That's what that's telling us. The chances of the second draw, what happened in the second draw is going to be affected by the first draw. So we found out this is dependent. So we're going to have to do the probability for given like we did before. We find the probability of, here we're doing drawing a 4 and a jack. So we're going to 4 and a jack. And I find that by finding the probability of the 4 first, and then find the probability of the jack given the 4, because we took a card out. There. So because of that given a 4, the chances of the jack change. Alright, so what's the chances of getting a 4? Well, the chances of getting a 4, there are actually 4 4s, right? Because there's 4 of every card in a deck of cards. There's 4 4s, there's 4 5s, 4 6s. So there are 4 4s out of the 52 cards. But when I go to pull my jack out, there's still 4 jacks because I pulled a 4 the first time. So given a 4, there's still 4 jacks, but there's only 51 cards left. So I do it like that. Again, 51 left instead of the 52. And you saw that every single time. When we did given like this, when it mattered, the bottom number always changes. It is possible for the top number to change. Maybe the case where you're trying to draw 2 jacks in a row. The first time there'd be 4 jacks, for the second time there'll only be 3 jacks. So it could happen where the top number changes, but the bottom number will always change when you do this. Okay, I'm going to go ahead and simplify this again before I multiply. So I'm going to divide this and get 4 divided by 4 is 1, 52 divided by 4 is 13. That way when I multiply, I don't have to do such big numbers. So I end up with 4 on the top, and I think this is the one that ends up being 663 again, because it's 13 times 51. So this one is being that 4 over 663. But again, this one was changed because the 4 got out of the deck, so there's less cards left. Let's try the next one. Here we're going to roll snake eyes, which is getting 1 twice in a row with a pair of dice. Is that dependent or independent? Well, it's independent. Like I said earlier, that dice rolls, coin flips, those are always independent because the first roll does not affect the second. You can't roll 1 the first time and that makes you have better or worse chances of the second one because the dice it doesn't remember what was rolled, it just rolls a new number. So this is independent. So when we do this one, we just find the probability of 1 the first time and the probability of the 1 the second time, and we just do them separately. We don't have to worry about the given. So we just find the probability of 1 and multiply that by the probability of another 1. So here you notice they're not any given. We're not going to worry about the given because the first roll does not affect the second roll. So what's my chance of getting 1? Well, there's only 1 on of the 6 sides on a die, right? There's only one on the 6 sides. Again, we'll say 6-sided dice. I really should put that in my notes. This is 6-sided, but and again, my math lab will probably use 6-sided die, but if they use anything else, they should specify, what the other die is. Probably 1, again, is 1 out of 6 because it doesn't change. The first die is not going to change the second die, so it's 1/6 both times, and we just multiply. 1 is 1. 6 times 6 is 36. And yeah, it makes sense. There's only 1 pair of 1s, right? 1 is the only option that's good out of the 36 possible combinations when you roll 2 dice. So we already saw that earlier. There's when you roll 2 dice, there's 36 options. Okay, last one here. At a university, about 45% of the students are freshmen. If you pick out 2 students walking down a hallway, what are the chances both won't be freshmen? Now, technically, this would be dependent. This is dependent because when I go pick 2 people, I'm not going to pick the same person twice. It would be 2 people then. That would be silly, right? I'm not going to pick the same person twice. So once I pick the first person, I'm taking them out of the pool of candidates, out of the people I could pick for the second. So because of that, typically you would call this dependent, But there's an exception. So, but for small samples from large populations, we can treat this as independent. So it's basically kind of a rule or a law that someone figured out that if you have a small enough sample size, a small enough collection you're picking from a big group, then you can say, well, I probably wasn't going to pick the same person twice anyways. The chances of that happening are so slim that I could ignore the fact that I'm excluding the person the second time. So if you're picking only two people from an entire university campus, if there's thousands of people in the university, then what were the chances you're going to pick the same person twice? Well, they're pretty much nil. They're very, very slim. So in that case, you can actually do it like it's independent. So we're going to treat this one as if it's independent. Even though, yes, technically, since we're picking two students and they have to be different, we're saying, oh, it's like drawing a card and not putting it back because you can't pick the card again. We'll treat it like it's independent, though. And that all that comes down to this whole small samples from large populations. You can just pretend like it's independent, like it doesn't matter. We'll see this actually pop up later in the semester because when you design surveys and stuff, when you're out there as a statistician and you design a survey and you want to go ask people your survey, if you do your survey for a small enough group from a large enough population, then we could use the math for independence, where we don't have to worry about the given probabilities, and it just makes the math a bit easier because you don't have to worry about that given aspect. So that's something people always worry about. Okay, if I pick a small enough sample from a large enough group, then it works. If my sample's too big out of the group, if I'm sampling like half the group, then I have to worry about repeated people. But if I pick a small sample from a large group, then I don't have to worry about it. Okay, so to do this, I'm just going to find the probability of, we're looking for won't be freshmen. Notice that this won't be freshmen. I'm looking for not freshmen and not freshmen because we want two not freshmen, right? Now, this is the case where the complement actually makes this a little bit easier because to do this, we'd have to find the probability of the not freshman first, multiply it by the probability of the not freshman second. We can use the fact that if there's 45% of the students are freshmen, so probably getting a freshman is 45% or 0.45, then we can do 1 minus 0.45 and give what is that, 55 to be equal to the probability of not a freshman. So there's that complement at play, right? We said the complement, if you know the probability of getting something, the probability of not getting it is 1 minus the probability of getting it. So, in this case, A would be freshman, complement would be not freshman, and so together those make up a whole, or 100%. So then we can just use 0.55 for both of these. 0.55 times 0.55, and that'll give us our answer. So here, because we don't have fractions, we're going to go ahead and just multiply these decimals. 0.55 times 0.55, and we get 0.3025. So the probability for this was 0.3025, or 30.25%, if you want the percentage. And again, it's harder to get two not freshmen than it would be just to get one not freshman. One not freshman is not a big deal because it's just 55% for one not freshman. But if I'm trying to get two that are freshmen, that's harder to do. It's always harder to do both. Okay, so we had and probabilities where we multiplied, but we have to worry about the given probability where the second thing might change. If it's independent, not so much, we don't have to worry about it, but if it's dependent, we have to worry about the second probability changing. And we talked about the OR probabilities, where we find the probability of each one and then subtracting the overlap. And again, if there is no overlap, then we don't have to worry about the subtraction part, but if there's something that's in both sets, you subtract that. So and OR probabilities are really common. A lot of times you can take a more complex or more difficult probability problem and you could break it up into smaller, easier pieces. If you could break it up into OR pieces or AND pieces. Like an example would be, winning lottery tickets. Instead of trying to figure out the probability of winning all the different prizes in the lottery, we might figure out the probability of each separate prize for the lottery and then say I'm happy with either any of those prizes because then I'll have a winning ticket, and I'll use an OR probability to add them all together. Um, or if I want to find the probability of all my tickets being losers, what are my chances I won't win anything? You have to buy 20 tickets, and I could use an and probability to say, okay, this ticket's a loser, and this ticket's a loser, and this ticket's a loser, and now make it a little bit easier to find the probability of them all being losers versus if they're, if I have to do it, in some more complicated way. So and or probabilities, the addition rule and the multiplication rule, really common things we use in probability because it helps us, break it down into easier chunks and do part at a time. Instead of doing the whole thing at once, we can break it down into parts separately. So that's it for 4.2. We're just finishing. We're moving on through probability. We've got a couple more sections of probability to go, and then we'll be done with this chapter. So I'll see you on the next one.